Hi, I'm Whitney Espich, the CEO of the MIT Alumni Association, and I hope you enjoy this digital production created for alumni and friends like you.
I'm really happy to be here to talk to such a group of MIT alumni. And I'd particularly like to welcome, I see a lot of those of you in red jackets here who were here on campus 50 years ago. And I hope that in addition to catching up with old friends while you're here, potentially you've been walking around campus and reflecting on how much has changed at MIT since you were here. And I have to say this is something that I understand quite a bit, standing here as an MIT faculty member, that things are different here at MIT now. When you graduated, the concentration of CO2 in the atmosphere was a mere 325 parts per million. For those of you in your 30th reunion, that was 353. If you're here for your 10th, that's 387 parts per million, and we've just graduated the class of 410 parts per million. Now, I didn't have the privilege of going to MIT myself, but I spent a little bit of time elsewhere in Cambridge during the 360s. And I did have the privilege of being advised by an MIT alum who was of the class of about 320, and you'll hear from John Holdren next. But I do have the privilege today of being at MIT and sharing knowledge for the last 20 parts per million or so with the classes of 415 parts per million and beyond. And this challenge, it's really great to be doing that at MIT because climate is really linked to so many of the world's great challenges. And MIT's mission specifically mentions bringing knowledge to bear on the world's great challenges. And in talking about climate change today, I'd like to focus on three main things. First, I'm going to argue that addressing climate change is really central to addressing any of these world's great challenges. It's intrinsically linked to our efforts to work, as MIT urges us to do, for the betterment of humankind. Second, the understanding of how climate is linked to human well-being is a challenge for science and engineering. It requires not only knowledge of the environment, but also knowledge of systems that also involve people and technology. And achieving this understanding, as we heard so eloquently from Professor Sadoway, is a matter of not only asking the right questions, but getting the right answers and getting useful answers, and engaging and partnering with communities, decision makers, and people like our alumni who are making change on the ground. So what are the world's great challenges? Well, one way to think about that, one effort to crystallize these was the effort in 2015 by the United Nations General Assembly to identify 17 global goals for the year 2030. This is the attempt to define what is that better world, to come to consensus on what kind of future we want. And one of these goals involves climate action. But climate action, as I said earlier, is linked to many. Climate change makes the other goals harder to achieve. And I'm going to give an example of one challenge that's both complicated by climate change, but also illustrates how action on climate can benefit people in ways that are concrete and help us address some of these pressing global problems. And these are related to the Sustainable Development Goals of good health and well-being and affordable and clean energy. And again, very much linked to climate action. And that is the challenge of air quality, so clean air and human health. So I'm going to focus on a major air pollutant, which is particulate matter, PM 2.5, atmospheric particles that are smaller than 2.5 microns in diameter that you can breathe in all the way into your lungs. And it's a major global health challenge. 9 out of 10 people in the world breathe unhealthy air. It leads to millions of deaths every year, and a large fraction of deaths from lung cancer, stroke, and heart disease, big contributors to mortality. So I'm going to focus on three questions. One, to ask how is climate change linked to air pollution that damages human health? What's the fundamental connections? How do we understand that? Two, what technologies and strategies can improve human well-being, both now and in the future? And three, how can research better inform action? And I'm going to be highlighting some of the work of MIT alumni who've worked with me from EAPS, from Earth, Atmospheric, and Planetary Sciences, from the Institute for Data Systems and Society, and from the Technology and Policy Program. So first, on how climate change is linked to air pollution that damages human health. We did a study a few years ago that really showed that without mitigating climate change, we can make air pollution much worse. And that is because climate change, the formation of air pollution really responds to what's happening in the environment in meteorology. And with emissions of regional air pollution precursors held constant, climate change, because of stagnation events, because of increased chemistry happening at higher temperatures, can lead to higher concentrations of health damages. So this hurts our ability to cut pollution, and we have to work against that. But in addition, we have some potential bonuses, and that is that air pollution and greenhouse gases come from common sources. Coal, transportation, producing power. I'm showing both China and the United States here to illustrate that this is really a worldwide challenge. And we can also think about other pollutants that result from fossil fuel burning. I work a lot on mercury. And mercury is dangerous to human health because it deposits to ecosystems. It gets released by burning coal, circulates worldwide through the atmosphere, deposits to ecosystems, turns into the neurotoxic methylmercury, and people are exposed by eating fish. It's a particular danger to pregnant women and children who see their neurotoxic effects. And since industrialization, we've seen the concentrations of mercury, this is in the Arctic, go up substantially. So how can we think about this question of how technologies and strategies can help address air pollution and climate, and in order to improve human well-being both now and in the future? And this is really what my research group here at MIT does. And we start from the idea that we not only have to understand environmental fate and transport, how the climate system is working, how air pollutants travel, and we use global scale and regional scale models to do this. But we also have to understand the technologies and emission controls and what the drivers of those things are, as well as the impacts on people and health, and the policy, institutions, and knowledge that connect all these things, the decisions that we're making as a society. And this is a complicated issue because it ends up being a pretty hard problem. You can think about this as a simple graph. There are things that you can do to make air pollution worse, and things that you can do to make air pollution better. And similarly, there are things that you can do that make climate change worse and make climate change better. A bunch of the technologies that we have right now, burning fossil fuels, that's going to both make air pollution worse and make climate change worse. On the other hand, we have new technologies, renewable energy, solar panels. That's going to improve air pollution. You're not burning anything that releasing into the environment, but also not releasing CO2 at the same time. Now, this seems to be a simple problem if you just look at those two axes, but it turns out there are technologies and there are strategies that exist on the other quadrants as well. Anyone have a Volkswagen? So efforts to improve the fuel efficiency of Volkswagen vehicles were done in ways that made air pollution from diesels worse. Efforts to reduce sulfur pollution from ships, sulfates in the atmosphere can have a cooling effect in some places in the climate. So efforts to reduce ship pollution could potentially, under some circumstances, make climate change worse. So we need to really understand these impacts and these different technologies. In addition, the formation of particulate matter in the atmosphere is nonlinear. So one example of that is inorganic components of particulate matter combine nitrates, sulfates, and ammonium. Nitrates coming from sources like cars, sulfates coming from sources like power plants burning coal, and ammonium coming from agriculture. And there's nonlinear processes that combine in the atmosphere to form particulate matter. Now, what we do as a society changes the formation and the different effectiveness of cuts in any one of these precursors at influencing the concentrations of PM 2.5 in the atmosphere. This is the kind of thing that we take into account in our atmospheric chemical models. And work of PhD from 2016 actually looked at this in the United States and how recent efforts to change, to reduce emissions in the United States have changed the ability of cuts in nitrates and sulfates to reduce PM 2.5. As Professor Karplus noted earlier, we can also think about the ways in which climate policies so putting a price on carbon, can benefit air pollution. And this is really important to think about what near-term benefits carbon policy can have that people can see, people can visualize. And Mingwei Li, who graduated this year, just this week, from Earth Atmospheric and Planetary Sciences, her work shows that under the Paris Agreement commitments of China, this will lead to almost a 12% decrease in concentrations of particulate matter, and that would lead to more than 90,000 premature deaths avoided. But we can ask even more complicated questions, and this is the case even in the US. So some earlier work we looked at asked the question of which kinds of US policy would reduce more local air pollution. Would it be focusing on power plants, focusing on vehicles, or just putting a price on carbon? What would happen? The policy we looked at was one that would reduce CO2 by 10% from 2006 to 2030. Now, that's a pretty small amount relative to the kind of magnitude of change that we would need to get to a goal of reducing climate change, keeping climate change below 2 degrees. But this is pretty much similar to, as originally formulated, what the Obama-era Clean Power Plan was, which aimed to cut emissions from the electricity sector by an estimated 32% below 2005 levels. And I will note that this morning also Maria Zuber noted that that was the Obama-era policy that inspired the MIT climate commitment. What we found was that surprisingly, all these different policies had very comparable benefits, all of them, no matter what sector you took carbon out of. You reduced particulate matter. But you had very different costs, which really reinforced the ways in which we can think about how to have the most benefit for local people. These had the same climate impact, but the same impact on almost the same impact on particulate matter, but air pollution benefits offset a different amount of policy costs because of the different costs of the policy. So as we think about how to optimize policy, we can think about how to balance and how to inform policymakers who are thinking about this. Now, this again was very close, the clean energy policy was very close to what was proposed under the Clean Power Plan. So one way we quantified that was using standard US regulatory methods and said, well, the net benefit of avoided mortalities would be $39 billion. Now, you'll note that in recent years, it's been proposed that the Clean Power Plan be rolled back. And those of you who did problem sets as MIT undergrads, all of you in this room, will know that sometimes you make a sign error really early on. And it's really disappointing when you get to the final answer, but it's easy to fix. You just have to go back and propagate that sign error. And this is what we come up with. It's thinking about what would happen if you rolled back some of those standards. So what we do see happening in the US is a lot of regional and state level action. And one of those types of actions takes the form of renewable portfolio standards or mandates that a certain fraction of regional power comes from renewable sources. We did a study looking at the possibility of strengthening some of those standards in the US. This was a study done by a 2018 graduate of the Technology and Policy program. And in his thesis, he looked at strengthening those standards and also compared those standards to putting in a CO2 price. And he found that strengthening renewable portfolio standards in the Midwest leads to health benefits of over $100 per ton of CO2. Transforming energy systems internationally could also have substantial impacts on mercury emissions. China is the biggest source of global mercury emissions. And mercury emissions are regulated by a global treaty called the Minamata Convention. If you control these emissions based on end-of-pipe control, so not dealing with the underlying coal problem, but just addressing the mercury before it enters the environment, you can get some benefits. Reducing, and this is for both China and India, China's in blue and India's in red, and the amount of mercury coming from the power sector reduces as you go to more stringent policy with these end-of-pipe controls. But if you undergo energy transformation, this can move all of that lower. And mercury controls have substantial health benefits. Domestic mercury controls can have billions of dollars per year in benefits, both domestic controls under the mercury and air toxic standards and international controls. And what we do to figure this out is we trace mercury through its transport in the environment and estimate what would happen when mercury deposits to ecosystems, builds up as methylmercury in fish, and what kind of fish people are eating from both nearby ecosystems as well as the global oceans to figure this out. So in order to think about this question in a practical way, we can think about how we can use this research to better inform action, to really work with those on the ground, to try to inject the best science as possible into these questions. And the work that we did to quantify the impacts of particulate matter under future climate, we worked with EPA back in 2015, who were interested in how do we mitigate this? How do we make better sense of what the benefits to the US would be if we mitigated climate change on air quality? So this was the summary that then EPA Administrator Gina McCarthy summarized. This was the report that came out of EPA based on our work, and projected that if you take action to mitigate climate change in the US, you could avoid 57,000 deaths from poor air quality associated with climate change. That's something that really resonates with the population here, right here at home, in terms of climate change in the nearer term. So what we're trying to do now is really make sure that the scientific message really gets across in the continuing legal framework. So I've worked together with climate scientists to make sure that the understanding of what these benefits of climate action would be are taken into account both in our legal and our legislative frameworks. And also worked internationally with the Minamata Convention on Mercury to think about how we can summarize the latest mercury science and inform international negotiations. And in that, I've worked together with a new effort at MIT called the Policy Lab at the MIT Center for International Studies. And the Policy Lab takes MIT research and really helps MIT faculty members communicate that and get that into the world of policy so that policy is better informed by the science that's happening here. And I'm also working together with communities as part of the MIT Superfund research program. Under the Superfund research program, we work with communities here in Boston, as well as in northern New England, some Native American communities, thinking about toxic pollution in their communities and how we can use science to inform responses. And in this, we really look to shape the questions that we ask and the work that we do based on the needs of these communities, working very closely together with them to try to inform the work that we're doing here. So yesterday in his talk, Mayor Bloomberg noted that climate change is not just a science problem. In fact, he said that winning the battle on climate change will depend less on scientific advancement and more on political activism. And he argued that this has gone from a scientific challenge to a political challenge. And while I agree completely with Mayor Bloomberg that this is a political challenge, this is not an either-or proposition. The scientific challenge and the engineering challenge and the social science challenge are intrinsically linked to the political challenge. And we really need to understand them together in order to make progress on this issue. Because when the class of 410 parts per million is sitting in the audience here and donning their red jackets, we need to know which class they'll greet. Will they be greeting the new alumni of the class of 450, of 500, of 600, or the class of 700 parts per million and beyond? And it's really up to us, both at MIT and globally, to determine which class they will greet in the future. Thanks.
Thanks for joining us. And for more information on how to connect with the MIT Alumni Association, please visit our website.